Welcome to Warwick University, where I'm joining astronomers from around the UK for our National Astronomy meeting. We're all about to witness, and I can't believe I finally get to say this, the first images from JWST. Welcome to the sky at night. The buzz in the room tells you that people are excited about this moment, a moment some people have waited 25 years for.
This is it. This is the day we get the first science images back from the James Webb Space Telescope, and you've got a front row seat to the cosmos. Wow, look at that.
Well, those images are stunning. They're iconic, they're intriguing, but most of all, they're just beautiful. What's really exciting, though, is that the telescope can now get on and start doing science. And I can't wait to find out what discoveries it's going to make. So this month, we've decided to hit the road, visiting astronomers who are getting their hands on JWST for the very first time. Come on, let's go. Don't worry, I've got it. Let's go. Come on. Now, while I'm off gallivanting around the UK, Maggie's back in the studio with a JWST masterclass.
It's taken over 20 years and $10 billion to design and build the James Webb Space Telescope, and is home to some of the most complicated scientific equipment ever built. With these tools on board, it will collect unparalleled amounts of data.
They say that the best camera is the one you have on you. Well, it turns out they were wrong. The JWST is an incredible feat of engineering, and I'm immensely proud to be one of the 10,000 scientists that worked on it. The amount of new tech we kitted the telescope out with is absolutely mind-blowing. But what really sets the JWST apart from the telescopes that have come before it is not just its size, but also the type of light it's observing. The Hubble Space Telescope is famous for taking breathtaking images here in the visible spectrum. However, the JWST will be observing the universe with longer wavelengths of light, here in the infrared. This means two incredible things for astronomers. Firstly, infrared light can pass through clouds of dust which scatter visible light. This results in us seeing galaxies and stars which have previously been shrouded from science.
And secondly, we can see some of the universe's earliest stars and galaxies to form after the Big Bang.
These early stars produced unimaginable amounts of energy and shone in the ultraviolet part of the spectrum. But as the universe rapidly expanded, it literally stretched the wavelength of this light. So if you want to see light from these early objects, we need to stop looking here and start looking here.
It's always great to see astronomy in the papers, and look, we've even made some of the front pages. But of course, by the time you're seeing this, these images, well, they're old news. Ow. So we're taking you right to the heart of the action. Today, we're going to visit Professor Andy Bunker. in the beautiful, learned, historic city of
Take the third exit for Oxford.
Oxford. When I first met Andy, I was still an undergraduate student, and he was already anticipating the images of distant galaxy clusters that he'd get from what became JWST. That was more than 20 years ago, so I can imagine he's particularly thrilled with this image. This is only the start for Andy and his team, though. Can't wait to hear what they've got planned. Well, Andy, let's start with this image that by now I think everyone watching will have seen. What exactly are we looking at here?
So this is an image of a cluster of galaxies. These are these yellowish objects here. And it's a rich cluster of galaxies, so much mass there, in fact, it's bending the light coming from objects behind that. And this is probably the most beautiful image so far.
So it's the galaxies person, but
yeah,
I mean, I agree with you. I think it's beautiful. Yeah. And these lensed galaxies are these are the distant ones, right?
That's right. So they're stretched into these arc-type shapes, and some of the reddest arcs are extremely distant objects at high redshift, so light left them when the universe was young, and it's been gravitationally magnified by this foreground cluster.
How far back do you hope to be able to see?
So with the James Webb Space Telescope, we're hoping to push back to redshifts of 15 or even 20. So this corresponds to the very early infancy of the universe. We're talking about the first few 100 million years after the Big Bang. So that's the first just a few % of the current age of the universe. So really this would be the not only the childhood snaps, but the baby snaps of the birth of galaxies. The first few images show that James Webb is really delivering in terms of sensitivity. So, you know, this is the high redshift frontier. You know, trying to push to the earliest stars and galaxies to form, and James Webb should be able to deliver on that. And we're going to find out in the next few weeks and months.
And this has been your part of the puzzle as well. You've been planning for a long time to use JWST to do this. Can you tell us more about the observations that you've got planned?
So there are big question marks over when the first stars and galaxies form in history, and can we chart how galaxies build up their stars, the rate at which they're forming stars. We can also chart the rate at which heavy elements are formed. So all the heavy elements we're very familiar with, oxygen, carbon, etc. They're made in stars over time, these big nuclear furnaces. And as time progresses, the matter from which subsequent generations of stars form gets more and more chemically enriched. There's a greater fraction of these heavier elements.
Because you're basically recycling, right?
So I'm involved with one of the instruments on James Webb called NIRSPEC, the Near Infrared Spectrograph, and this spreads the light out at infrared wavelengths. So we're actually able to measure the chemical enrichment through this technique of spectroscopy. And if we can chart at how rapidly not only stars are forming, but how rapidly the material is enriched chemically, this tells us a lot about the formation and evolution of galaxies.
And ultimately about us as well, of course. We've been through, the sun went through this process.
Yeah, that's right. Without previous generations of supernovae, there'd be no life on Earth, I think.
Right. So tell me about this first generation of stars then, because there's some reasons to believe they might be very different.
So one of the, probably the holy grail of my sort of research is to try and find the first generation of stars that formed out of the primordial soup left over from the Big Bang. We're looking for a signature which has hydrogen and helium, but none of the emission lines of the heavier elements such as oxygen, carbon, etc. James Webb will be able to get the spectra to confirm them.
This is getting ridiculous. So we've just been talking to Andy about the earliest galaxies in the universe. I look online and there's a paper from a group of researchers with new JWST data that might have captured some of those galaxies. Here they are. They look like blobs, but they're exciting blobs. These might be the earliest galaxies we've ever seen. Now, the paper's not reviewed. We'll have to do follow-up, but it does show you how fast things are moving. Now we've got JWST.
One of the major decisions the engineers designing JWST had to make was where to position it in space. The solution was to place it in orbit at what is called the second Lagrange point, or L2. For JWST to see the faintest light from the cosmic dawn, it needs to be far away from Earth's contaminating radiations. For instance, if you're trying to take a picture of the night sky,
with a bright light bulb beside you, you won't see a thing. Ooh.
Far enough away, in this case, is 1.5 million kilometres. Here, at the L2 Lagrange point, JWST's forever home, the telescope actually orbits the entire Sun-Earth system.
At this point in space, both the Sun and the Earth are in the same relative position to the telescope. Here, the JWST can keep our star and our home planet on the right side of the sun shield, providing an SPF, that's sun protection factor, of around 1 million. In the shade, JWST can reach its functioning temperature of 7 degrees Kelvin or minus 266 Celsius. Only at this chilly temperature can the telescope detect the remnant heat of exploding stars thousands of light years away.
Some stars really save the best till last, and we saw that in the most surprising of last week's JWST images, this one of the Southern Ring Nebula. It's the detail that you can see in the gas structure around this dying star that astounds me. Not bad going, given that it's 2,500 light years away. And it's that detail that excites Dr. Mika Matsuura, who we're going to go and see next. She studies dying stars like this one. Well, thanks for joining us to talk about these wonderful results from JWST and what we're going to see in the future. The image on the screen here is a planetary nebula, but what is that?
The planetary nebula is the dying phase of low mass stars, typically the mass of the sun. So when they're going to die, what's happened is they're going to so-called red giant phase, which become very large. And because it's so large, gravity is not really strong. So when sometimes just star puff up, gas from the star just release from the star surface of the star, and then lose gas and accumulate in time.
Why is the infrared good for looking at planetary nebulae?
So there are several reasons. One of the reasons is because when these gas are lost from stars, they also make dust. And dust from these stars are an important source of dust you can find in space, in cosmic time, maybe. So that's why they are really interesting to see how much dust has been ejected from this type of stars. That is one of the reasons. But actual surprise of this object is actually the structure of molecular hydrogen.
So when I couldn't believe the amount of structure when I saw this image for the first time. Were you surprised, or is this what you thought this would look like?
No, I didn't expect, to be honest. So this is a big surprise to me. Yeah, so this, I don't know why, but molecular hydrogen is made of so many small clouds, probably about a million of them. So it's amazing to see them. Yeah.
Tell me about your own research. So you're part of the team that's looking at planetary nebulae with JWST. What else are you hoping to see? What other objects are you looking at?
Okay, so the other object I'm studying is called NGC 6302, but it's telephone number. So actually, it's often called butterfly nebula.
Oh, okay, yeah.
So it has a really nice two bipolar outflow coming from the star, and there's a so-called central disk. And what we believe is, with this central disk, that's maybe made slightly different from usual environment in astronomy. So we don't know exactly why there's a disk, but we do know there should be disk from this image. What we are going to get is a spectrum, but JWST can make a spectra simultaneously across many spots across. So we can cover entire disk in just, one shot. And
get conditions in the disk and off the disk and in different parts of the
yes.
disk. Right, and we want to understand the history of dust in
yes.
the universe for all of this, because it's dust you make planets out
of. Hopefully.
yeah, hopefully. Well, I can't wait to see the butterfly nebula.
Hopefully.
Good luck with your data.
Thank you.
And come back and tell us about it when you've got your beautiful images.
Mika can do her research because of specialised instruments on board the JWST called spectrographs. These instruments split the light into different wavelengths, enabling scientists to identify the different chemical components that make up their target objects. For astronomers, this is a quantum leap forward.
Collecting infrared light from distant stars shrouded in gas is one thing, but being able to split that light into a spectrum of colours, like a prism splits the white light into a rainbow, changes the game entirely. Looking at light spectra allows scientists to determine the temperature and chemical compositions of the objects being observed. The light from every object can be spread into a spectrum. Now, while the Hubble Space Telescope could do this, it could only do one object at a time.
JWST, on the other hand, can look at up to 100 spectra at a time.
And it does this in a few pretty incredible ways, one of which is the micro shutter array.
This nifty tool works by opening or closing a combination of 250,000 minuscule doorways, so that it blocks out everything in the field of view, apart from certain points of light in the sky.
Not only can JWST learn about direct sources of infrared light, like stars and galaxies, but it can also use the technique to learn about clouds of dust and gas that the light has passed through and interacted with. Observing light in this way is called spectroscopy, and this technique is perfect for analysing the atmospheres of exoplanets.
We're back on the road, and today it's west to Bristol and exoplanets. Now, when I was at the National Astronomy meeting last week, the biggest reaction wasn't to the images that JWST released, but to this spectrum of exoplanet WASP 96b. While it's not a beautiful image in itself, it's telling a story, chapter and verse, of an exoplanet more than 1,000 light years away that was previously a blank book to astronomers.
So, Chris, why is it called WASP?
It's not great, is it? I always think if there are aliens, they're going to be really annoyed to find out they come from WASP 96b, but they're named after the telescope or the project that found them. So WASP is the wide-angle search for planets, 96 is the star, and B is the second thing in the system. So A's the star, B's the first planet. TRAPPIST, which is a famous system, is named after the beer, because it was a bunch of Belgian astronomers. So we should look for beer-loving aliens coming from there. Now, you might remember Dr. Hannah Wakeford from our episode last month when she was talking about using sunsets to study the atmospheres of exoplanets. That's exactly what she's using JWST to do, capturing light that's travelled from a distant star through the atmosphere of an exoplanet in its planetary system, across interstellar space and onto the telescope's detectors. We're on our way to see Hannah now because she's downloading new JWST data as we speak. I can't really believe she's stopping what she's doing to talk to us. Well, Hannah, we're all excited to see this spectrum, but how do you use JWST to look at exoplanets?
So the way that I use JWST to look at these exoplanets is through what is called the transit method. So we're actually looking at the star. We're not actually looking at the planet itself. We're inferring its existence by seeing over time how it affects the light from the star.
And that's what this graph is showing, right? This is the change in brightness.
But what we're seeing right here is the planet starting to pass in front of the star and blocking out some of that light.
So this is a game people have been playing with ground-based telescopes for ages. Have we got any JWST data yet?
Yeah, we've got some really exciting data from lots of different instruments and lots of different planetary systems. And this is one that I've been working on earlier. This is from commissioning data. So this is what they were doing to test how good this telescope was. So it's actually one of the worst observations that we will see from JWST, which is very exciting because you can already see just from the data without any kind of tricks and whistles done to it, this beautiful transit event. So we're looking at the star here. So we've got the star here, and then the planet comes in front and blocks out that light.
Naively, I think, if I think about a planet going in front of a star, I think a planet's a nice solid thing. It shouldn't matter what colour I look in, it's going to block out the same amount of star.
Right, but some of that starlight is actually able to shine through the planet's atmosphere before it reaches the telescope, just like we see with the sunsets. If you look at the Earth, you see through the Earth's atmosphere from something like the International Space Station, you can see the edge of our atmosphere and the starlight shining through it. That's what we're measuring. We're measuring the sunset around these planets. And the more atmosphere they have, the more light can shine through it and the more information we can get. I mean, we saw it right from the release images. And what we're seeing here is exactly that, the spectrum of the planet's atmosphere as that starlight has passed through it.
Okay, so this is sort of the amount of light that's trapped by the planet's atmosphere.
And what we're able to see here is that we've got this water, but it's not as high as we expected.
It's not blocking as much light as you expected.
Yeah, exactly. The amplitude, the difference between the bottom here and the top here is smaller than what we would have predicted for this world. And that actually tells us there's some kind of thing blocking it. And
something extra.
Yeah, something extra in the atmosphere. And the extra things we have in the atmosphere are clouds. But on this planet, we do not have water clouds in this atmosphere. The clouds in this planet's atmosphere are actually made of what we're standing on Earth, rock, magnesium silicate, sand, glass. So in this atmosphere, you have liquid droplets of glass suspended as clouds.
It's quite cool.
It's pretty amazing. So we're going to be using the mid-infrared instrument to look for the absorption signatures, the bumps and wiggles of liquid glass in the atmospheres of these worlds. So I'm really excited to prove that actually, yes, the clouds in this atmosphere are made of these magnesium silicates, the rock that we're standing on.
So you've been planning these observations with colleagues for a long while, I know. How does it feel to finally have data sitting on this computer?
Overwhelming. I'm getting all teary. Every time I think about it, I'm just like, this is so amazing.
JWST is home to some of the most complicated scientific equipment ever built that will keep scientists busy for decades to come.
For any space telescope, the instruments are the beating heart.
JWST is fitted with a suite of instruments that can observe a specific range of wavelengths, part of the electromagnetic spectrum.
JWST's four main instruments view light across the infrared spectra, from near-infrared to mid-infrared. These instruments produce a variety of data in the form of images and spectra. This is important because the wavelength that an object emits light at is very much dependent on the amount of energy it's producing. Most of the stars we see in the night sky are producing a lot of energy and can therefore be seen in the visible spectrum. But because the JWST's instruments are looking beyond visible light at infrared light, the bright stars we see with our eyes will fade from view, and cooler red dwarf stars will become clearer. Moving to longer wavelengths, even these cooler stars will start to disappear, and will start to pick up radiation from planets, asteroids, and even dust sprinkled between the stars.
For our final stop, we're visiting an old friend of mine in Leicester. So far, we've spoken to experts who study far-flung galaxies, stars, and exoplanets. But Professor Lee Fletcher's targets are closer to home, our own solar system's gas giant planets. When we started this road trip a week ago, Lee didn't have JWST images of any of his targets. But then, just a few days ago, this image of Jupiter was released. And what I love about this image is that it shows an old friend in a new light, with Jupiter's belts and the Great Red Spot glowing in infrared light. And just think, we're going to get infrared images like these for Saturn, for Uranus, for Neptune too. Lee must be exploding with excitement. Let's go and see what he's got planned. Well, Lee, we got a bonus JWST image and an early image of Jupiter, and it's magnificent.
So this was one of the first images that were released in a tranche of data from JWST. But what's happened since then is all these talented citizen scientists have been going into the database and trying to enhance these, make them look even better. And there's one that I saw via social media just a few days ago. So there's a lot going on in this image, including stuff that we don't understand just yet. Now, I'll give you an example. Do you see this fine line that's all the way around the right-hand side?
It's almost like somebody's put a cup down and there's a coffee stain around
it. You know, honestly, we all wondered, could this just be something that's we're misinterpreting? But the more we've looked at it, the more we've played with it, it does look like this is a real feature. And that blew us away. But I can tell you that the spectroscopic program from JWST, this is just a couple of images stacked together, actually taking spectra will be the smoking gun to tell us the answer to what that feature is.
It's great you've got new questions already, but we're of course looking at the planet here in the infrared with JWST. How different is the planet in the infrared from the optical?
For me, as someone who's worked with data from Jupiter and from Saturn over the years, the mid-infrared, longward of 5 micron, that's where the science really starts, because there you're measuring temperature, you're measuring gaseous abundance, you're measuring properties of the clouds, and you can say things about the climate and the dynamics of Jupiter's atmosphere.
And that is, of course, the plan. Tell us about what JWST is aiming to do in the next year or so with Jupiter.
So Jupiter was chosen as a target particularly because it's so big and so bright and it's moving and it's rotating. So this is a challenge for any observatory, let alone one that's brand new and we haven't used before. And what we're going to be doing is trying to look at all the aspects of the Jovian system to get a little bit of science, but also to feed back to the observatory and to the community how to use this facility. Or in my case, I'm going to be tracking and mapping the Great Red Spot.
But for that, you have a much smaller field of view. We don't always get to see the whole planet like we do here.
Yeah, JWST has got these incredible spectroscopic instruments on there, but their fields of view are so small that the Great Red Spot only just fits. So this is Jupiter, okay?
Very nice.
There. So it's rotating from west to east, okay? So the Great Red Spot is going to go from the dawn side, across the centre, and then off to the dusk side. It takes about 5 hours to make that transit. Now, Jupiter's bright, so you think, well, it's not going to take very long to get an exposure, right? That's where you'd be wrong, because Webb is so complicated in how it has to change its gratings, change its settings, shift wavelengths in order to assemble a full spectral cube takes the better part of 5 hours. So to create a map of the Great Red Spot, you have to catch it on the eastern limb, to catch it in the middle, then you have to catch it on the western limb, and that's what makes these observations quite difficult to stitch together.
So tell us about the other planets. What will we see?
Uranus is coming up in August and September. Saturn is coming up in October. And Neptune, we're going to have an opportunity to do that in 2023, so about 12 months. It is a tremendously exciting time, and it's going to keep us with sleepless nights and heavy workloads, I think, for at least 5 or 6 years to come, I would say.
Well, it's been an incredible trip, but it's time to leave our astronomers to enjoy their new telescope, and I'm excited to see what they discover. Now, you may have noticed that we didn't see Pete this month, but don't worry, next month he'll be telling us all about the wonders of astrophotography. Oh, and then the month after that is our annual Question Time show. And if you'd like to send a question to our expert panel, then go to our website to find out how to do so. Until next time, good night.
And Robin Ince are back with a witty look at the world through scientists' eyes. The new series of the Infinite Monkey Cage podcast. Listen now on BBC Sounds.